Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
How do we get around space? To get around space, we use rockets, right? We need a rocket. What is a rocket? Rocket is just a device or machine that accelerates gas. Gas is accelerated in one direction, and the vehicle, the reaction to that expelled gas moves in the other direction. It's basically Newton's third law of motion. What really happens in a rocket is you have combustion products produced in a combustion chamber. Those hot gases expand against the nozzle. So as the hot gas expands, it hits the nozzle, pushing against the nozzle, thus pushing the engine in one direction and whatever it's attached to, which is the vehicle, and the gas goes in another direction. Action, reaction. That's how rockets work. So what kind of rockets do we need to explore space? We actually need two types of propulsion systems to explore space. One, a launcher system, some massive launch vehicle, which is mostly fuel. These things develop millions of pounds of thrust to put into orbit the tiny payload up top here. Space shuttle, and this is a Delta IV Heavy, they lift the spacecraft into orbit. It's the spacecraft that you lift into orbit that actually carries out the mission. And so these things take off with sound and fury, impressive sight. They're mostly lifting their fuel. They're not carrying much into orbit. Actually, 25 tons is about as good as it gets, but they weigh on the order of 1 million pounds. Once it's in the lower orbit, it has to deploy the spacecraft that's going to actually carry out the mission, the payload, right? And so once the payload is deployed, the payload needs some kind of propulsion to carry out the rest of the mission. So we now have identified another type of propulsion. It's called onboard propulsion. So we need a launcher system to get into orbit. Then we need propulsion on board the payload to carry out the rest of the mission. Now, it turns out that onboard propulsion is very important to the mission. It effectively determines what you can do during the mission itself. The efficiency of an onboard propulsion system is even more important in that it determines the lifetime of the mission. It also determines how much payload you can actually have, because it turns out propulsion systems, the engines are light, but most of the mass is in the fuel, the propellant. And so if you have a fuel-efficient onboard propulsion system, you can do a lot. You can add more transponders, more instrumentations to make measurements. And you can also save on launch costs because you're not launching as much into orbit anymore. And the going rate is still around $10,000 per pound. So it's expensive to launch into space. So with efficient onboard propulsion, you can, rather than use a Delta IV Heavy, you can move down to a smaller launch vehicle, which saves cost. Now, onboard propulsion is the area that plasma thrusters, plasma engines are playing the biggest role. They're essentially game-changing in terms of what missions you can actually carry out. This is a NASA graphic here, which shows some of the functions of onboard propulsion. Some of it is obvious, right? For example, your vehicle has been launched into low Earth orbit. Now, let's say it's a probe that needs to go to Mars. So you need some kind of propulsion on board to take you to Mars. And if there's a sample return, you need some propulsion to get back. So that's relatively straightforward. So primary propulsion is one function of onboard propulsion. Another function of onboard propulsion is maintaining the orbits of satellites. It turns out that geosynchronous satellites, they orbit the equator at 22,000 miles or so. But those satellites are tugged on gravitationally by the sun and the moon. This tends to cause the satellite to drift either north and south of the equator. Now, the purpose of the geosynchronous satellite is to stay over one spot essentially and transmit. Well, if it's drifting, then your signals are going to drift as well. So you need some form of propulsion to offset that, and that's quite important from a commercial standpoint. Also, for those satellites that orbit to Earth at low altitudes, their orbits are susceptible to orbital perturbations due to the fact that the Earth is lumpy. This rotating globe here is essentially a color picture of what the acceleration due to gravity looks like as a function of position. It varies as a function of position because the Earth isn't homogeneous. Well, these variations in acceleration due to gravity perturbs the orbit, and you need some form of propulsion to take care of that. Orbit transfer is another application of onboard propulsion, and actually this week we had the Dragon capsule rendezvousing with space station. Its engines had some problems. They didn't turn on, and in order for the Dragon to catch up to the space station, in other words, change its orbit so it can catch up to the space station, those engines had to work. So they were able to get those engines online and they docked, and so far the story is having a happy ending. Dragon also uses those, the onboard propulsion on the vehicle to also deorbit that vehicle. And the final application for onboard propulsion is drag makeup. If you're low orbiting a vehicle like the space station, there is some drag, so you have to reboost every now and then. And as far as budgets for propulsion from a mass standpoint, these are Earth observing satellites here. This is the fraction of mass associated with the propulsion system. So it's about a third to a quarter to a third. Geosynchronous satellites, it's huge. More than half your vehicle is propulsion, and that's mostly fuel. Geosynchronous satellites are essentially hogs in terms of how much fuel is required to keep them there. They have 15-year missions, 15-year lifetime, so they need a lot of fuel to do the station keeping. And planetary, which is the more exciting missions, require almost half as well. And so if we developed a way to improve the efficiency of the onboard propulsion, we can reduce these mass fractions associated with the propulsion and allow more of the mass to be associated with payload, so you can do more and also extend the life of the mission. And so how do we quantify the efficiency of a rocket? Well, you may have heard of this term already, but efficiency of rocket is defined by a parameter we call the specific impulse. So in words, rather than go through those equations just loosely and crudely speaking, specific impulse is the thrust you get per gallon of fuel you expel out of the rocket per unit time. And that's what this is saying. So it's thrust over the mass flow rate, that's the m dot, times acceleration due to gravity. Thrust itself is the product of the mass flow out of the vehicle times the exhaust velocity. And so if we combine these two equations, plugging the thrust into this expression, we see that the efficiency of the rocket, the specific impulse, actually scales with the exhaust velocity. So when you're talking about specific impulse, you're really saying what the exhaust velocity is. So it's exhaust velocity divided by the acceleration due to gravity, which is about 10. So multiply specific impulse by 10, you get the exhaust velocity. So efficiency, higher the exhaust velocity, the higher the efficiency of the rocket. Back in the early 1900s, a school teacher by the name of let me make sure I get his name right. It's Tchaikovsky, Konstantin. Somebody got it? Tsiolkovsky. Yes, he's the father of modern rocketry, but he derived an expression known as the rocket equation, and that's what's shown here, which relates the exhaust velocity of the rocket to the mass of the rocket before you burn your fuel over the mass of the rocket after the fuel has expended all of its fuel. So basically, that his equation, the famous rocket equation, tells us if we need a certain delta V For our rocket to achieve a certain delta V, it has to burn a certain amount of fuel. And the amount of fuel that you have to burn is intimately related to the exhaust velocity, because the higher the exhaust velocity, the smaller this mass ratio has to be. So if we go over here and just rearrange this equation, this one's more intuitive. Basically what it's saying is for a given delta V, our change in velocity of the spacecraft, the mass required to achieve the mission grows exponentially. And so if the change in velocity that you require for the mission is much larger than your exhaust velocity, then the mission essentially becomes impossible because the mass ratios become fantastically too large. And delta V is important in that for every mission, there is an associated delta V. There's a delta V to get from the surface of the planet to low Earth orbit. There's a delta V to get from low Earth orbit to the body you're trying to reach. There's a delta V required, a fuel burn required to slow the vehicle down so that you can go into orbit about that body. So total delta V is quite important, and for missions to outer planet, the delta V's are large, and if that delta V is much larger than the exhaust velocity, then the fuel required to carry out the mission becomes almost prohibitively too large. And so we have a demo to illustrate the rocket equation, because the two things to take away from the rocket equation is the following. One, in order to achieve a mission with minimal amount of propellant expenditure, you need a high exhaust velocity. The second thing to remember is that in order to achieve a certain delta V, you have to expel mass. And so this demonstration is bottle rockets, and what Monica's going to do is she's going to launch two bottle rockets. One's going to be filled with mass, essentially air, and the other bottle rocket, she's going to add additional mass. And so, and that additional mass is of course water. And so basically what we're looking at is the mass ratio. The mass ratio for the rocket with the water is larger than the one with the air. So you can expect what's going to happen when she launches these two rockets. So the air rocket, so take it away, Monica.
Here's with no water, it's just air inside it. 3, 2, 1.
Small amount of mass, low thrust. So rocket equation in full effect there. So the interesting thing about the rocket equation, though, the change in velocity is related to that mass ratio, but it turns out because it's a logarithm of the mass ratio, even as you add more and more mass, the increment of delta V that you get is still going to be small. It's going to grow very slowly. So that's why those launch vehicles have to be so massive. You need enormous, fantastic amounts of propellant to carry out the mission. But we notice that the exhaust velocity is proportional to the change in velocity of the vehicle is proportional to the exhaust velocity. So that's a knob that we can turn, and that's where plasma propulsion comes in. So to put some of this into perspective, though, I did want to show you, just to calibrate you to what delta V's are important. These are delta V's for various missions. And for the interesting missions like the Jupiter, Uranus, and Saturn, the edges of the solar system, interstellar precursor type missions, 250 AU, large delta V's, but large relative to what? Well, the best we have in terms of chemical rockets is Space Shuttle main engine. It's 4.5 kilometers a second. Now, if you look at what's required for the interstellar precursor mission, it's 120 kilometers a second. So 120 divided by 4.5, and you take that to the exponential, you get something fantastically large, like 10 to the 11. So you can't do it. You can't do it. And you might say, well, Voyager did some interesting, carried out a very interesting grand tour, and it was all chemical. Well, it was partly chemical. It did a lot of gravity assist. The reason why Voyager was able to carry out a mission like that is because once every 175 years or so, the outer planets are aligned such that you can swing around all those planets and actually do a flyby. And that's what Voyager did. So with chemical, we can wait for every 175 years to do another flyby, or we can look to do something a little bit better, and that's what we're here to talk about. But first, why aren't chemical rockets any good? What limits the chemical rocket? Why can't we get higher delta V's with chemical rockets? Well, it turns out that there's only so much energy that can be released from chemical bonds. Once you break those bonds, that energy goes into, well, you break the bonds in the combustion process. That energy goes into accelerating the gas and expands against the nozzle to produce thrust. It turns out that there's a theoretical limitation to how much energy that you can get from a chemical reaction, that which is stored in the chemical bonds, and that ends up giving us an upper limit on the exhaust velocity of around 5,000 meters a second or 5 kilometers a second. The shuttle's main engine is already 4.5 kilometers a second. So we're essentially there as far as good as it gets from chemical rockets. Also, chemical rockets, there's no separation between the energy source and the propellant. It's all happening at once, so we can't control the amount of energy going into the propellant. So we have those limitations, and that's why we have to look to something else. So chemical is out. Our subject is going to be electric rockets. You can use nuclear reactions as well, and if time permits, we'll actually talk about those. But so our focus is on chemical rockets, and that's what we're going to, it's Enterprise with impulse drive, pointing us the way to electric rockets. So now, finally, plasma propulsion. So I'm going to use the word electric propulsion and plasma propulsion interchangeably because actually electric propulsion is a category of rocket science, and plasma propulsion is a subset of electric propulsion. They use electric energy. Electric propulsion is a facet of rocket science that deals with those engines that generate thrust by electrical means. And the beauty of electric propulsion is that your energy source is electrical in nature. It can be derived from solar energy, nuclear energy, or radioisotope energy. The energy is separate from the propellant. So I can add arbitrary amounts of energy to my propellant to accelerate the propellant to arbitrarily high exhaust velocities. I'm only limited by special relativity. So it's possible to get fractions of the speed of light in terms of exhaust velocities. So the usual approach in electric thrusters, and let's just turn this on, is to put gas into the engine and then apply electrical energy. And when we do that, we ionize the gas and producing a plasma. Plasma is known as the fourth state of matter, and what plasma is a collection, a soup of electrons and ions with the capacity for collective motion. We can exert forces on the plasma using electric and magnetic fields to accelerate it to arbitrarily high exhaust velocities. And these tubes here illustrate the application of electrical energy to a gas, and it's a proprietary blend, and we get these nice streamers, and you're welcome to take a look at these after the talk. So essentially, you make the plasma, and then you accelerate the particles to produce the thrust. So the key to electric propulsion is that you can get exhaust velocity some 10 to 100 times that of chemical rockets. So all of a sudden, you kind of break the rocket equation wide open. Energy emissions that was seemingly impossible become possible. But there is a drawback, if you want to call it a drawback, and that is that the thrust of electric propulsion devices tends to be low. It's in the millinewton to newton range, and it's about 4.4 newtons to a pound. So these are low thrust. And you might ask, why is it low? Well, it turns out to produce a plasma efficiently, you have to do it at low pressure. And typically the pressure inside these engines is something on the order of 1,000,000 times below atmospheric pressure, and even lower. And so the mass flow out of the engine is going to be correspondingly low, so the thrust is low. Also, you got to carry your energy source with you, but that's not a big deal because to do interesting missions, you need electrical energy anyway. So you need to carry the power supply with you anyway, especially if it's a planetary mission. So the takeaway is here, chemical rockets. Most of your space probe is propellant and electric propulsion. You only have a tiny amount of propellant that's required to carry out the mission, and so you have more payload there. And so there are many advantages, such as reduced launch costs and increased payload fraction. And so all of a sudden, missions that had reduced lifetime or were virtually impossible can be done. Look at the cost savings in terms of propellant mass that you gain with a geosynchronous satellite. It's greater than 50%. And so now companies, all communication satellites are going all electric now because of the savings. You can add more transponders or transmitters to your communication satellites. A mission like Neptune Orbiter that we talked about at the very beginning, you can carry a lot more hardware. You can carry like landers with you all of a sudden. Missions like the Interstellar Precursor or Pluto Orbiter, you can't even really do with chemical. It doesn't even show up on the graph. Now, you might say low thrust. Well, chemical rockets can still win the race to get to the target, but it turns out chemical rockets run for, say, minutes, and then they've expended all of their propellant, and then they get on a trajectory to intercept the planet. But the electric propulsion, the plasma rockets, fire continuously. And because they're firing continuously, they're continuously gaining speed. So the rocket equation doesn't say how long it takes you to get that delta V. It just says that this is the amount of propellant required to get that delta V. And so at high exhaust velocities, it may take longer because you're sending out, your mass flow is low, but over time, say a year, you can be moving substantially faster than a chemical rocket and you can actually beat it. So these exotic missions now, all possible. This graph shows these really high post-launch delta Vs approaching 100 kilometers per second. You can't do these with chemical. I mean, you're talking about a sample return from Neptune, a Kuiper Belt orbiter, Europa sample return, only with plasma thrusters. With chemical, all you can do is flybys. And then there's a low delta Vs down there. So there's that 10 to the 11. And so electric propulsion itself, as far as the engines go, are broken up into essentially three categories, which depends on how the thrust is actually produced. So what we've done so far is sort of motivate why plasma thrusters. They produce extremely high exhaust velocities. Now we're going to look at how some of the technologies work. So the three categories include electrothermal, electrostatic, and electromagnetic. And so as the names imply, it tells you how the thrust is produced. Electrothermal devices use electrical energy to heat the propellant to produce thrust. So these devices are the most primitive of the plasma rockets, but you notice here that you can get up to 1,200 seconds of specific impulse. And you compare that to the state-of-the-art chemical rockets, which is around 400, that's still pretty good, right? You're 3 times that. Electrostatic use electric fields to accelerate the particles to produce the thrust. The ion thruster, which is my favorite engine, it can produce the highest specific impulse of all of these thrusters that we have on the table. And you can use those for space science missions. Look at this, 15,000 seconds. You're talking about 150 kilometer per second exhaust velocity. Remember, some of those exotic missions required only around 100 to 120, so you can do those missions. The electromagnetic accelerators are compelling because one engine can process a lot of power, which means that it can produce a lot of thrust. The downside is that our development of these engines is they're not as advanced, they're not as mature, and in the coming years we hope to change that situation. But they are very high power devices, and they are also capable of producing fairly high specific impulse, up to 10,000 seconds or 100 kilometers per second exhaust velocity. So now this is where we sort of take a look at each engine and how they work. So we start with electrothermal devices. So what I have up here is a resistojet and an arc jet. Now a resistojet basically is not even a plasma thruster. You flow gas through the device. There's an electric heater that heats the gas up and expands the gas through a nozzle to produce thrust. These devices began a revolution in communication satellites, though, because communication satellites had all that propellant on in the form of hydrazine to station keep, the north-south station keep. And what they discovered was if you pass the decomposed hydrazine gas through a resistor to heat it to even higher temperatures and allow it to expand out of a nozzle, you can increase the specific impulse a bit more. You can go from, say, 200 seconds specific impulse to 300 seconds. So that's a huge propellant mass savings. The arc jet is a true plasma thruster. It utilizes an electric arc, so you apply voltage between the cathode and then this annular anode here, and producing a high intense arc. The arc has temperatures in the 5,000 to 6,000 degree Kelvin range, and so gas flowing through this hot arc is heated to high temperatures, and that expands against a nozzle to produce thrust. The first arc jets flew on communication satellites starting in the early 90s. AT&T was actually the first one to have an arc jet on board. That ushered in the era of true plasma thrusters on communication satellites, 1,000 second specific impulse. Now, of the thrusters that we have discussed so far, these thrusters rely on basically heating the gas and allowing it to expand through a nozzle to produce thrust. The electrostatic and electromagnetic thrusters don't have physical nozzles. The thrust is derived by the interaction of the plasma particles with the electrodes. That's where the reaction force takes place. So what you have in these engines are beams of charged particles flowing out that you've accelerated, and reaction force is felt by the vehicle through the electrodes. And so the first engine that we're going to talk about is an ion thruster, and we have an antique ion thruster that was loaned to us for the purpose of this Saturday morning physics. So this is an actual thruster that its sister actually flew in 1970, and you're welcome to come up and take a look at it. But how ion thrusters work, we have a schematic up here. Ion thruster has essentially 5 parts. What you have is a hot cathode, you have an anode electrode, a gas ring to inject xenon gas. Xenon is the propellant of choice. It is very expensive, but it's easy to ionize and it's heavy. And we have grids as well, and an external cathode. So how does this device work? Since that's up there, I think I can point at least. So this is the cathode. These are the grids. This chamber is the anode. This is the propellant tank. And if you come up, you'll be able to see the gas feed ring as well. But so how does it work? So gas is injected into the chamber. The cathode is activated. The idea is for the electrons emitted from the cathode to hit gas molecules to make ions. You impact, ionize the gas molecules. Now, the pressure inside these engines is very low. Remember, I said you're talking about some million to 10 million times below atmospheric pressure. So normally, when you send electrons into a low pressure environment like this, they just go straight to the anode. They don't make any ions at all. And so somehow we have to coax the electrons to hang around long enough until they run into a gas molecule and ionize it. And the way we do that is we apply a magnetic field. And so on the outside of this device, are these black things you see here are magnet rings, and these are the magnetic field lines. So what happens is when an electron crosses the path of a magnetic field, it experiences a force that's perpendicular to both the direction that the particle is traveling and the direction of the magnetic field. So that forces the electron to execute circular motion or circular orbits. What this does in effect is it increases the electron's resonance time because it has to undergo a lot of spirals before it makes it to the anode. So while it's hanging around, spiraling around on its way to the anode, it may run into a gas particle and it'll hit the gas particle and produce an ion. So the name of the game is to design the magnet such that we increase the likelihood that the electron can hit something and ionize it, and we do that by essentially increasing the electron's resonance time. So we produce a very dense plasma as a result. We have grids here. The grids are engineering marvels in themselves. So this is a 1970s grid that you see here. It has about 870 holes. The grids in modern ion thrusters have over 15,000 to 20,000 holes. So imagine a plate that's about a foot in diameter, has about 15,000 apertures, millimeter-sized apertures. The spacing between the two grids that accelerate the ions is only a fraction of a millimeter. So it's an engineering marvel. And so each one of those holes accelerates out an ion beamlet. And those little ion beamlets coalesce to form a total ion beam. Now, if you're just extracting ions out of this chamber, electrons are left behind, so it charges up negatively, right? And so the engine will stop running in about a microsecond. And so we have to pump those electrons out, and that's what the cathode outside here does, is it actually extracts electrons out of the chamber and pumps them into the ion beam to neutralize the ion beam, because the ion beam would spread out as well because of repulsion. You saw a positive space charge. But when you neutralize it, you produce a well-collimated beam. Now, so this is just up to show you the motion of charged particles in a magnetic field. So what we have here now is a neat demonstrator that shows you how a magnetic field can increase the resonance time of the electrons, forcing it to execute long paths so you can actually make plasma inside the chamber. So I'll take this off, and what you see here is a bulb containing helium gas. There's an electron beam shooting straight up. There's no magnetic field at all here. So I don't have any current on that magnet coil. Now if okay, so it's shooting straight up, and that's what happened in ion thrust. Electrons go straight to the anode. No resonance time. But it is glowing. The pressure inside the globe is higher than that in an ion thruster. So along the path of the electron, along the path that the electrons take to the wall, it does produce some ionization. But it's a small amount. It's just along that path. But as we increase the magnetic field, we can force that electron beam to spiral, and notice the globe is starting to fill with plasma. So along the pathway, we're making more and more electron ion pairs, making more plasma, and the whole bulb itself is filling with plasma. That's what happens in the ion thruster. The magnetic field forces the electron to execute complicated orbits so that they hang around long enough to ionize the gas and fill the chamber with plasma. So that's how we get high ionization efficiencies, even though we're 10 million times below atmospheric pressure. And when you do that, you produce a nice plasma inside the device. The high voltage electrodes extract the ions to form a beam. And so I have a collage of ion beams that actually the folk here at Michigan, we've had opportunity to work on. But I want to bring your attention to this one. This is NASA's next ion thruster, so it's NASA's evolutionary xenon ion thruster. This engine has been operating for over 46,000 hours. That's almost 5 years. It's processed 850 kilograms of xenon. Right now, this engine has demonstrated the capacity to do just about any planetary mission that you can conceive of. This engine is still running. And so for comparison purposes, chemical rockets run for tens of minutes at the most. We have an engine that gives you a gentle thrust you can essentially trust for years. So this is, next category, next electrostatic ion thruster is the sort of nemesis of the ion thruster. It's its competition. It's called a Hall thruster. And the thing about the Hall thruster, let's put up a graphic that shows better how it works. The Hall thruster doesn't have grids. So the grid actually serves as a mask. So you can't extract all the ions in the chamber because you have a physical mask there. Hall thruster doesn't have a grid at all, so it can produce higher thrust at similar power levels. But its lifetime isn't as long. It can't run 46,000 hours. No way. You're talking about less than half that. So how does a Hall thruster work? So it has three parts. It has a cathode, hot cathode. It has an anode with a gas feed, an electromagnet. The electromagnet produces a radial magnetic field that you see here. And so basically what happens is we apply voltage between the cathode and anode. The electrons want to go to that anode, but they encounter the magnetic field. And electrons have difficult time crossing magnetic field lines. And because of that, there is a voltage drop that develops in the region of the magnetized the region where the magnetic field is. So we sort of trap the electrons there. In fact, we end up with an electron cloud circulating in this channel where the magnetic field is appreciable. So we have electron cloud here, and we have gas flowing from the anode. It has to pass through the electron cloud. So what's going to happen? They're going to hit the ions. The electrons are going to hit the gas molecules in the electron cloud, producing plasma. The ions are accelerated in one direction, and the electrons go in the opposite direction. So you get an ion beam. Electrons from the cathode neutralize that ion beam as well. So the cathode neutralizes the ion beam as well as it makes the ions. So it's a simpler system as well. You need only one cathode. So it has that going for it too. And so the jury's still out on which makes the most sense for space science missions. But if you want to go to Pluto, you got to use an ion thruster, a gridded ion thruster. So here's a picture of some plumes. This is actually an engine being tested by Alec Gallimore's group here at Michigan. This is my old branch chief sitting by two engines. If he was here, he'd be quite embarrassed right now. But this is a 75 kilowatt device. You can use this for human type missions all of a sudden because you can produce newtons of thrust, and that is impressive. So the last thruster we're going to talk about is the pulsed inductive thruster. Pulsed inductive thruster is an electromagnetic accelerator, and we'll quickly talk about how it works. And we have a demonstrator for that. But it's sort of a monstrosity when you look at it, but it has only three parts. It has a flat coil here, a capacitor bank, and a nozzle. So how does it work? Well, we first inject gas through the nozzle. That gas is pointed downward. It hits this flat plane here where the coil is. We then discharge those capacitors. Now, when you pass current through the coils of that, coil, what's going to happen? When you pass current through a coil, you're going to get a magnetic field. And that magnetic field is time varying. The magnetic field is time varying. And by Faraday's law, a time varying magnetic field will make, just think about generators, an electric field. That's right. So an electric field in this device is very strong. In fact, the electric field is strong enough that it ionizes this gas and produces a plasma, a ring of plasma. That electric field also forces current through that plasma. But the current through the plasma is moving in the opposite direction the current is moving through the coil. So if I have two wires with current moving in opposite directions, what happens to those wires? They're going to attract or repel. Well, opposite direction. It's opposite your intuition. They're going to repel. They'll repel. If they're going the same direction, they actually come together. And so it pops. The plasma ring pops off. It's accelerated in the opposite direction. And so we have a surrogate for a pit thruster over here. Basically, what we have here is over here in the middle, this apparatus, we have a coil Well, I should just stand over here. We have a coil and a stalk with essentially an iron core. And basically, when I flip this switch, I pass current through the coil. That produces the time-varying magnetic field, and that can induce a current to go in my surrogate for plasma here. And what happens is that time-varying magnetic field induces electric field. Electric field drives current through the coil in the opposite direction that the current's moving through the coil. So it's going to experience a repulsive force, and it'll fly off, just like in the pit thruster. So pit thruster, you pulse it, you make the plasma ring, and the plasma ring is accelerated off. The vehicle goes in one direction, the plasma ring goes in another direction. That's the reaction force. So what we're going to do is fire this thing, and hopefully I'll be able to catch it and not hit that glass bulb there. So we'll kind of angle this because this thing kind of flies. So this is actually how the pit thruster works. This is real. The conductivity of plasma is close to that of metal. So here we go. And so that's exactly how pit thruster works, but you do that at a frequency of about 50 hertz. So it's pop, 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 and so it's a putt-putt kind of engine. But but you can develop high thrust, and for human missions, this makes sense. So we talked about how they work. So now, what about how are they being used right now? It turns out that if you go back to 1985, not many plasma thrusters were flying. Actually, for commercial applications, there were none. All you had was these resistor jets that we talked about because they saw the cost savings that you get with the resistor jets. So, but if you zoom to 2010, Aerojet Corporation hasn't updated it, but now the sky is starting to darken with spacecraft that have plasma thrusters on board. We have almost 240 satellites in orbit right now that have plasma thrusters on them. Does anybody have DirecTV? Anybody? One person? Two? So when you're sitting watching your DirecTV, you should take comfort in noting that that geosynchronous satellite that's transmitting your DirecTV signals has ion thrusters on board that provides a north-south station keeping to make sure that those signals are pointed to where they should be pointed. So DirecTV satellites have ion thrusters on board, the ion thrusters that we just discussed. So we have a lot of electric propulsion on board because people realize you could add more payload because of the high exhaust velocity you get with electric rockets. And so now the best for last, so we're going to go do a whirlwind tour of some interesting missions. And so I won't go through all of them, but I will touch on the really important ones. And so let's take a look. So the first real demonstration of a plasma thruster for a space science mission occurred when Deep Space One mission was launched in 1998. That mission had a 30-centimeter ion thruster on board that basically had a max power of 2.3 kilowatts, the thrust level 92 millinewtons, specific impulse range broad but up to 3,100 seconds, xenon, and the delta V that it imparted to the vehicle for the whole mission was 4.5 kilometers a second. At the time, that was a record. No chemical rocket, no rocket of any kind had done that. Remember, the chemical rockets usually for space science missions is gravity assist. So the engine ran for over 15,000 hours in space, and in the process, it flew by an asteroid and a comet. The first target was a flyby of an asteroid called Braille, and if you look at that asteroid, you're like, man, that doesn't look like much, but it actually flew within 9 miles of the surface of that asteroid. And you might ask, why is it so small? Well, it turns out that the asteroid was so small and so dim, the cameras on the Deep Space One spacecraft didn't see it until it was too late. And by the time it realized it was in the vicinity, it began to turn its cameras, but it was moving so fast, it could only snap this picture of this corkscrew-looking asteroid. And the thing about that asteroid, it's like people believe that it's a piece of the asteroid Vesta. So that's why it's so irregularly shaped. But it did fly through the tail of Comet Borrelli and took a lot of data. It took the pictures of the active nucleus, and there was some concern that it might damage the spacecraft as it flew through the plume of this asteroid. So it was a successful mission. It kind of opened the floodgates to people using plasma propulsion for space science missions. The next one we're going to show is a Smart 1. That was the European Space Agency. That involved a 67 millinewton, 1 kilowatt Hall thruster. Basically a spiral to the moon. It was a technology demonstration mission, and they were able to do very high resolution mappings of the moon and also mineralogy. They ultimately crashed the spacecraft into the surface of the moon to look at the flash and use spectrometers to see if there's water on the moon. It turns out there's a lot of water ice on the moon, but that was a successful mission as well. The delta V for that vehicle was 3.7 kilometers per second. So probably one of the more exciting and drama-filled missions that has happened in recent times was the Hayabusa mission by the Japanese Space Agency. This was an ambitious mission. The goal of this mission was to fly to an asteroid, land on the asteroid, extract a sample from that asteroid, and then return that sample. And so everything was going well. I was using 4 ion thrusters, actually microwave thrusters, not hot cathode thrusters. The thrusters were low power though, but they used 4 of them. So 8 millinewtons apiece, 350 watts of power. And so they made it to the asteroid, and here's a shadow of the vehicle over the asteroid. You can actually see the solar rays and the body of the vehicle itself. And so they touched down, left it off, they touched down again, and that's when the trouble started. When they touched down again, they were getting ready to leave. Everybody was happy. This was like going really well. And then somehow the fuel tank for the chemical rockets on board ruptured. It ruptured, and they lost all the fuel, the hydrazine propellant. The reaction control wheels also was lost, and that thing drifted in space for almost a year. They thought it was over. We thought it was over. It was like, oh man. But it turns out that they didn't give up. Eventually, they got the spacecraft to recover, and they had no chemical propulsion, but they used the ion thrusters and the xenon fuel in the ion thruster to serve as reaction control and primary propulsion, and they were able to get back to Earth. So basically 3 years in limbo, but they made it back, and they have samples of the asteroid to prove it. And so that was exciting. But at the time, a lot of people was really worried at JAXA. So ongoing right now is this mission, Dawn. Dawn is a mission to 2 of the largest planetoids in the solar system, and that is Vesta and Ceres. So these are massive mini planets. And so this spacecraft is going to basically is going to these asteroids to explore them. And by explore, I don't mean a flyby. The idea is the spacecraft goes to an asteroid, goes into orbit around the asteroid, studies the asteroid, leaves the asteroid, goes to the next asteroid, enters orbit about it, and studies it. This has never been done before. All other missions have been flybys or single destination. This is the first 2-destination mission, and you can only do this with plasma propulsion because of the fuel efficiency. And so it uses the same engines that the Deep Space One mission used, except it has 3 on board this time. Only 1 operates at any given time. There's 3 for a lifetime. And so so maybe you've seen the pictures, but it has already visited Vesta. It explored Vesta for almost a year. It left Vesta this past summer, and now it's on its way to Ceres. And Ceres has water on it. And so this should be interesting when it finally arrives at Ceres. So this is Vesta before dawn. That's the best image we had of Vesta. It's about 300-mile diameter asteroid after dawn. That's impressive. It was in orbit around it. And this is Itokawa. That's the asteroid that the Hayabusa mission visited. It's about 540 meters. You know it was small when you could see the shadow of the spacecraft on the asteroid, and you can see the rest of the asteroid as well. That puts it in perspective. So this is Itokawa. There's a little dot in the middle of this circle here. And this is Vesta. So it puts it in perspective the size of Vesta. So it's kind of like NASA's bragging rights. We visited a much big asteroid. And this is a nice visual of the studies of that Dawn spacecraft as it orbited Vesta. So pretty cool pictures, a lot of nice detail. Now, this is a future planned mission. This is Fetch. So this might sound interesting. So NASA's studying Fetch. So the idea is to go to an asteroid, grab the asteroid, and bring it back to Earth. But we're not going to land it on Earth. We're going to bring it into orbit about the moon. And so the idea is you bring it to orbit around the moon so you can study it. And so the concept of doing something like this is old. So the father of modern rocketry said that this is one of the tenets for conquest of space. You have to utilize the resources in space. There's been a lot of movies about living on asteroids, and there's a book, Mining the Sky, how we expand into the solar system. We utilize the resources. There are companies now talking about mining asteroids. So this NASA mission is not too off the wall. And here are some reasons why we'd want to do it. Well, first, the science. If we bring it close, we can study it up close, right? It also, and this is kind of weak and thin, but it does give astronauts something to do if they're if they're going to be sort of moving around in cislunar orbits anyway. And but this. The capture, transfer, and examination of asteroids for planetary defense is probably the biggest reason why one would want to endeavor something like this. Because if you can go to an asteroid, grab it, and move it around, then you can prevent an asteroid from hitting the planet, right? You can actually bag it up and move it away. Or at minimum, you can attach yourself to that asteroid and push it out of the way. So that's important. And finally, you can develop methodology to mine resources. So if it's close, we can do a lot with it. And so the asteroid that blew up over Russia in February is a stark reminder of how important it is for us to understand composition of these asteroids. And you know, if something much larger than that hit, I mean, it could be catastrophic, right? So if we detect it and we're able to move it away, we can save ourselves, right? You can do it with electric propulsion. Also, we haven't really brought much back to Earth in regards to extraterrestrial material. We don't want to wait until the stuff re-enters the atmosphere and hits us, right? It's better to go and grab it and study it. The most we've taken is the Apollo missions. They almost 500, 382 kilograms of moon rocks. There's a mission that has been paid for that will happen. It's a sample return mission to an asteroid. It's called OSIRIS-REx, but it's only going to bring back 60 grams. This mission, Fetch, is going to bring back a 500,000 kilogram rock. 500. Now that's more massive than space station. And just for perspective, something about this size is what we're kind of talking about. So how do we do it? Well, you can't really do this with chemical rockets. It just takes too much propellant, and I'll show you why. But this is the spacecraft configuration. Massive solar arrays, about 75 square meters. This is the vehicle, and this is the bag to capture it in. It's funny, but that's the only way to do it, right? You have to have a bag to put the asteroid in. And so you leave Earth and you do a gravity assist. Then you use the plasma thrusters because they're fuel efficient to drive to the asteroid. You bag it up, and it's the same airbag technology that was used to land the rovers on Mars, Opportunity and Spirit, Opportunity and Spirit. So it's the same technology. So we have that technology, and that's the way it should look if you were looking out there. You scoop it up, bag it up, and bring it. We have the technologies to do it. The baseline is Hall thrusters, but we can easily use gridded ion thrusters. The bagging technology we have, and solar array technology is mature, so we can actually do this mission. This is a nice graphic. It shows how much mass is required to do the mission if you use chemical rockets. This is nitrogen tetra oxide monomethyl hydrazine route, and this is LOX, and this is electric propulsion. So this is in tons. This is the mass required that you need in low Earth orbit to do the mission. So your spacecraft has to have this much chemical fuel, about 361 tons of it, 225 with this, and electric propulsion, 18. The launch capacity of Delta IV Heavy is around 25 tons. So you can put the entire electric propulsion spacecraft on one expendable launch vehicle. If you do it chemically, you're going to have to use multiple launches and assemble it in orbit, which makes it prohibitive. So, okay, so I want to just throw this one out there. Maybe just if you spare me just a few minutes. Another interesting mission is called New Worlds Observer that uses a plasma thruster system that next to rocket engine. New Worlds Observer uses a ion thruster to point a star shield or star shade. And basically, the purpose of this mission is to image planets outside our solar system. The problem with using space-based telescopes to image planets outside our solar system is that the light from the star washes out the image of the planet. Well, if you have a specially designed star shield, the starlight is obstructed, but the light from the planet, which is very dim, can actually pass through, and you can image the planet. The purpose of the ion thruster is to point the star shield to the various targets and to maintain the orbit of the star shield. And so this is a mission that NASA is looking at, and it is a possibility, but it can just open up the planets outside of our solar system as far as imaging, directly imaging them. And anybody know about Babylon 5 at all? Yeah. Okay. Doesn't that look like the shadow vehicles on Babylon 5? It's just, I don't know. When I first saw Starship, I thought about that. So we can also, in closing, we can also use these engines to explore, to actually propel humans to asteroids as well, or even to Mars. We're developing high-power rocket engines to do that. NASA's studying a mission where plasma thrusters will drive a spacecraft to a nearby asteroid, and they rendezvous with the asteroid and do operations on that asteroid. So this is one where we don't bring the asteroid to us. And finally, in closing, the future of plasma propulsion. The future of plasma propulsion, in my opinion, is nuclear. So whereas you can get tens of thousands of seconds of specific impulse with plasma rockets, if you have a nuclear reacting plasma in which nuclear reactions are taking place, either fusion or fission, you can have specific impulses in the millions of seconds. And so this is a graphic that shows inertial confinement fusion, where you have a hydrogen pellet. You compress it to thermonuclear conditions, and plasma fusion burn ensues. You release that nuclear energy. You have very high velocity particles evolving from that. So it's a basic deuterium, tritium, and you get energetic alpha particles as your accelerated particle. And another way is to have a plasma of uranium that's fissioning. Well, when particles fission, they come off with very high, couple hundred MeV type energies, and that translates into significant fractions of the speed of light. And so, if you can sort of funnel this energetic plasma with a nozzle, you can develop high thrust and also high specific impulse. And the nozzles in this case can't be physical. You use magnetic fields or magnetic nozzles to channel the thrust. And we have two artist conceptions of how these engines will work. This is one in which the plume is fissioning plasma. You don't want to be behind an engine that's spewing out fission fragments. It was a radioactive, but that's a whole another discussion there. But this is one VISTA. It was studied by Lawrence Livermore National Labs, where little mini fusion explosions take place behind the vehicle. The plasma expands against a magnetic nozzle that's attached to this particular vehicle, and it pushes it along. So it too is a sort of a putt-putt type of engine. So this is my, in my opinion, this is the future of truly advanced plasma propulsion. And so that's it.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.